Okay, I guess it's time to have a look at our problems that I posted the other day. Let's start with number one, this crevasse thing. So we have 2 points, point 1 and point 2, and we saw this crevasse in certain directions. And then later on we realized, okay, actually our compass was not adjusted for the magnetic declination. So we need to keep that in mind when we draw our location on the map. I printed out the map a little bit differently than what I posted. I think that's maybe a bit easier to see on camera. So here's point 1 and point 2. Point 1, our bearing that we measured was 352 degrees. And then for point 2 we had 316 degrees. Magnetic, so just as a reminder, in some maps you'll find these compass rose, or it's just find magnetic variation or declination somewhere in the notes. In any case, it shows you that the magnetic north is off from true north, and our maps are all constructed with true north. This is where the meridians point to, it's grid lines here, and so that's what we need to basically compensate for. And normally do this in a compass. I have a compass like this, where you can see the outline that I try to align my needle to is tilted, so this compass is correctly adjusted for Iceland, 8.5 degrees west. And then you can read off the true bearing here on the outside scale. But we didn't do that, so basically we made a measurement like this, so we're off, and we need to do a little bit of math to correct for that. So conveniently we have the magnetic variation here also printed. It's 8.5 degrees, 8 degrees 30 minutes. There's 60 minutes in a degree, so 8.5 degrees that we have to subtract here. So 316 degrees minus 8.5 is 307.5 degrees, and here 315. So that would be magnetic, that would be true. 352 minus 8.5 is 343.5 degrees true. And these bearings we can now use to draw our sidelines here. And you know, this doesn't go to 300 degrees, so I'm just to basically a bit of a cheat here. I can either use a vertical line here and read off the grades here, or I can use horizontal line and read it off here. So let's do it like this here. So then 316 degrees, 307 degrees would be 52 degrees, 15.5 degrees, like so. And do it like that. Okay. So I need to, of course, align the 0 here so I can read off the degrees here, and then also make sure I go as close to the center of this point as possible. 52.5. Alright. That looks good. So now Thomas Island here. I'll make it a bit longer just in case, since I'm not sure where exactly we're going to land on the map. Like so. Okay, so we know from this point we saw the crevasse somewhere in this direction, and then from here it's 343.5 degrees. That would be 16.5. So I'm sure I can read it off somewhere. Not finding a good place here. See, not getting there. Okay. So then we have to use a horizontal line. Does this work? 73.5 then? Okay, it doesn't work. I have to do it from here. Okay, so now I can read it off here. 73.5 degrees. 3.5. All right, and then our desired location is here on the intersection. So that's our point where we saw the crevasse. Now the next question is, how far would we be off if we just had ignored this declination and tried to use our bearings as they are? Well, we can just basically go back to 8.5 degrees and see what happens. I'll use black here. So then we would be kind of looking in this direction here, and 8.5 here. So that would be then our mistaken location, and we would be off by about 1.8 centimeters, which if you just try to line it up here real quick, that's about 250 meters, right? So this is, each block here is 50 meters. So 1.8 is 5 blocks. That would be off by 250 meters. Quite a bit. Now, can we really read off bearings that accurately? Not really, right? Again, if you look at our compass, you'll see that the gradations here are only even degrees, so that's 2-degree intervals, and that's really also how accurately you can really try to align the compass needle here with this outline. And with other compasses it's similar. Since we're all just in the outdoors with relatively small compasses like this one, you have to try to be really accurate, and still I don't think you can get much closer than, let's say, 2 degrees or so, right? So yeah, just keep that in mind. There is always going to be some error, especially when you're sighting for things that are pretty far away. So for example, here, this point is 11.5 centimeters away. 11.5 centimeters. That's more than 1,500 meters, right? 11.5. That's 1,600 meters away. So yeah, we're now going to be super accurate with this. Okay, now finally the last question here is to estimate the longitude and latitude of this point as accurately as we can. And so we already have a grid that we can use for that. So we know that the longitude is going to be between 15 degrees 55 minutes and 15 degrees 56 minutes. That's of course not really very accurate. It's still a pretty large span here, and similar for latitude. Now, of course, we have a ruler, and it would be nice if we could just, read up the divisions here and get more accurate. But if we just align our ruler like so, that is not very convenient. That's not a good subdivision here to work with. Would be nice to have 10 centimeters here maybe. So then we have 100 millimeters. We could read off hundredths of a minute, since we have full minutes here. How can we get 10 centimeters here? Well, we just tilt our ruler like so. Or actually, maybe it could be a little bit better like this. I think we can see it more accurately like so. Right, we tilt our ruler. So we have 0 here, we have 10 here. So we have now 10 centimeters or 100 millimeters. Can we get the intersection? Ah, we're just outside here. But yeah, we're okay. I think that's still gonna work, right? So we read off here 73, I want to say. $74 maybe? Let's go with 74 millimeters, right? and we already know the full degrees in minutes, so that's 15 degrees 55 point, and this 100, so 0.74 minutes west. That's our longitude, 15 degrees. And now for latitude, we have to be careful because our parallels here are half-degree grid lines, right? So this is 15.5, this is 16. So now we don't need to do a little bit of math because we start counting basically at 5, and then we cannot just keep counting because it's not very convenient. So we'll still divide it by 10, but then we have to keep in mind that every intersection here is basically only a half step, so we need to divide whatever we read off here by 2. And also we have to be careful that we start reading in the right direction, so we start from here reading upwards. So 0 is here, put 10 up there. Make sure we try to get really the center of the intersection here. Alright, so let's just use the other color here. So that's 34 millimeters, and then that's divided by 2 is hundreds of degrees, so that's 0.17 minutes, and then we start at 6415.5, so basically there's another 0.5 or 15.5 that we have to add here, so that's 15.67 minutes, right? Okay, so in total we have 64 degrees and then 15.67 minutes north. That's our point here. Okay, so how accurate were we with our drawings here? Well, the way I created this problem is that I had this known location on the map, and I put it in the computer software, and then I put down 2 hypothetical points, and I calculated which directions we would see this point from these 2 locations here, right? And so exactly where this point is supposed to be, and I have it here on a little note, and that is it. So we were off by basically 100th of a minute. That's about 10 meters maybe, right? That's pretty cool considering we just used a piece of paper, a ruler, and a pen. Okay, so the next problem is this thing about reading off longitude and latitude, and the question is whether or not this is enough information to actually pinpoint a location. And let me just grab some other piece of paper here to write down. Okay, so let's see how we can interpret this digits in various ways, because we don't know if this is decimal degrees. Then it would be 64 degrees. No, sorry, 64.02279 degrees. That's what I meant to write. Decimal degrees. 64 is the full degrees, and then the rest is just after the decimal point. North, obviously. And then 18 degrees. Making the same mistake again. 18.01934 degrees west. Okay, but we can also read this as degrees and decimal minutes. So it would still be 64 degrees here, right? But now this is all the degrees, and then the rest is minutes with 2 points 2 digits full degrees and the rest decimal. So 64 degrees, 02.279 minutes north. And then same here, 18 degrees, 01.934 minutes west. And then finally it could be degrees and minutes and seconds. Right? And so then this is 64 degrees, 02 minutes, 27.9 seconds north. And then longitude is 18 degrees, 01 minutes, 93.4 seconds west. Okay, now we can, just reading this off or looking at these digits, we can immediately exclude the third option here, because just like minutes, seconds also only go from 0 to 59, right? Because 60 seconds is a minute, 60 minutes is a degree, so you cannot really have 93 seconds here. Although much software and GPS devices let you put this in and they automatically convert this. That allows you to do some simple math basically, and they can tolerate this, but they would never display it like this, right? So display would always be correctly between 0 and 59 minutes or seconds. All right, so we can exclude that option for sure. That's not happening. But so we still have either degrees or degrees and minutes. And how much of an error would that be if we kind of mistakenly use one or the other? So how much can we expect there? Well, we have to do a little bit of math for that. If we just look at the latitude here, it's either 64.0227 degrees, or it's 64 degrees 02.279 minutes. So the question is, well, the 64 degrees are the same, right? So we can just ignore that part. And so the question is, how far apart are 0.02279 degrees and 02.279 minutes? Well, we already know that there is 60 minutes in a degree. So if we want to convert both to the same, we can just multiply this one here by 60, and then we'll see what that is in minutes. So let's do that real quick. Just use my phone. Quick calculator here. So we have 0.02279 times 60. So that is 01.367 minutes. And so the difference between those is how much? That's 2.279. So the difference is 0.9116 minutes. Okay, now how much of an error is that in reality? And that kind of ties into the final question: how many meters does 1 minute of latitude or longitude roughly span in Iceland? Well, that's pretty easy, because 1 minute of latitude minute of is exactly 1 nautical mile. So that's exactly how a nautical mile is defined. A nautical mile is a distance that 1 degree of latitude covers, and that's about 1,800 meters roughly. And 1,800 times 0.9116. So let's take my phone again. 1,800 times 0.9116. So the distance is, so the arrow in latitude is about 16,640 meters. There's also an error in longitude, but that is less because if you think about how the meridians so if this is the Earth here, right here is the North Pole. These are the meridians here. They all converge at the North Pole, right? So at the North Pole, if you're up here somewhere, the difference is going to eventually come to 0. And at the equator, it's its maximum. And in Iceland, we're about half in between. So here, 1 minute of longitude is probably around 800 meters. Give or take, right? And we can also read it off here on this map, right? So we can see this is 1 meter of longitude here. That's 5.8 centimeters. Let's put 5.8 centimeters up here. 5.8. So we have 500 here, and then we have 600, 700, 800. That's pretty close to 800 meters, right? So 1 minute of latitude, again, that's about 600 meters, 1,600 meters. No, sorry, 1,800 meters in latitude and 800 meters in longitude. All right, and for our final question here, we're walking over Vatnajökull, and we know that eventually we have to make a turn, but we don't really want to use our devices too much as we approach this turn. And the question is, okay, can we rely on some other methods to judge our distance that we're covering? And it's pretty obvious what I'm trying to say here. I think it's good to have an intuition for how many steps you're taking with various methods. If you're hiking, if you're snowshoeing, cross-country skiing, if it's up or downhill, like how long is your stride length, and what is your step frequency, so how many steps are you taking per second or whatever, and then you can use that information to give you a guesstimate for, okay, how much longer do we have to walk, and are we getting close to these locations. Steps are a pretty fun way to track things, even without actively having any of our devices log our activities, because like watches here, our phones also, they'll count steps in a very energy efficient way and basically do it all the time anyway. So even if I'm not like tracking, I can just read off, okay, now I have 6,500 steps, and then I'll walk for a little while and I'll say, okay, now I have 7,500 steps. I just made 1,000 steps. That's maybe 500 meters that I've just covered, and so forth. or I know, okay, I've been walking for 20 minutes, I roughly take a step every second. 20 minutes, it's 1200 seconds, so I've taken roughly 1200 steps, and so forth, right? So just something to keep in mind when we're out guiding, and just, you know, consciously like maybe tracking these things when you have devices active, and then just store this away in your mind so you can later recall, okay, that's how many steps I usually take to go up this and that, and so forth. All right, so that's those 3 questions. I hope that was informative and interesting, and hope to see you next time. Bye.